Let's start with a little bit of terminology. If I ever see a simple number, we typically refer to that as a constant, and if I was going to use a typical letter, I'd use C for constant. If I set it equal to y, either y equals c in general or y equals 3 specifically, I would get a horizontal line at whatever the value of the constant is. All the y values would be, in this case, 3. So let's look at something a little bit different. Suppose that I have an expression like 2x minus 5, or ax plus b. This is called a linear expression. Now, in one sense, our previous graph, y equals 3, was a line, but it was a constant line, a slope of 0, and it can never be anything except that constant value of a 3. But if I have something like y is equal to 2x minus 5, that expression can attain any value at all, similar to what we talked about when we talked about the absolute value function. So in this case, that would have an intercept of a negative 5 with a slope of 2. I could generalize and say that that's y is equal to ax plus b, but would see that this is a line that can attain any and every value possible. So for that reason, this term of x is often called the linear term, because when that term of x appears, I don't get a constant line that can only attain one value. I now have a linear expression that can attain any value at all. Now, by the same token, if I have a second power expression, this is where we get the parabola. So let's just specifically make this now a y equals statement, and this is why we call this a quadratic expression. Quad prefix typically means 4. So you now see that we have 4 terms. Or if this were an equation, say 0 equal to x squared minus 3x plus 7, the equation has 4 terms. That's why when we see the second power term appear, we often refer to this as the quadratic term. Now that can be just a little bit strange, because if I had x squared is equal to 4, that's still considered to be a quadratic equation, not because there are 4 terms, but simply because there is a second degree term in the expression. Or if I have the graph of y is equal to x squared, the simple parabola parent function, that's still considered to be a quadratic graph. And so quad generally means 4, and if I see the general expression, it will have 4 terms. But just to note, if I have an expression that has an x in it, that will always be referred to as linear. So the expression of x is called the linear term. And if I have a second degree term, I always call that second degree term the quadratic term. So that terminology is now going to be in play, because if I look at a polynomial expression, just as a simple example, let's look at this example down here. This is called the quadratic term, the x squared, and the plus 8x is called the linear term. Now that's going to be very important, just terminology, to understand what we talk about now. So we're going to try to create a standard form equation and put it back into the form of the vertex form. So here's a simple example. This is x squared plus 4x, but it needs a third term. So we're thinking in this way. So I'll do a little bit of enlargement just to make it easier to write. We're thinking that there could be some expression of x in a binomial that's squared that creates x squared plus 4x plus 4. Now, you can read the notes, and it's a little more formal expression, but here's what you're supposed to notice. Whenever we expand the binomial, we always say first term squared twice the product. The number that I'm about to write in this position here is going to multiply the x and then double to become the 4x that I see right here. So simply put, I just need to reverse the doubling process. This must be a 2. And it must be a plus 2 because of this expression here, having an x squared plus 4x. Now, if you've been practicing expanding binomials, that'll make perfect sense to you. Moreover, you know that there must be a 4 that's right here. Now, the number that I'm going to put in these blanks is called the term of completion. It is the constant that would cause the trinomial to be the result of the squaring of one binomial. So we would consider x squared plus 4x plus 4 to be a square trinomial. Similarly, if you think about numbers, is 8 a square number? Well, in a sense, yes, the square root of 8 can square to make an 8, but there's no whole number that squares to make an 8. But 9 is considered to be the square of a number. 9 is the square of 3. So we're looking for something that can be a nice whole number that we can put in this third position that causes x squared plus 4x plus this number to become a perfect square. Now here's a little thing that I always say whenever I'm going through this process, and it is just something that can help me to remember what I'm going to do to create the binomial square and the term of completion. When I square a binomial, I say first term squared is twice the product, second term squared. When I'm doing this process here, I always say half in square out. Now here's what that means. It means that the number inside my parenthesis, the 2 over here, is always half of the linear term, the expression, the coefficient of just the x. Half of 4 is 2. So half in, square out. When I expand the parenthesis, the term of completion will be a 4. So if I just use that simple little technique there, half of 6 is 3. The square of 3 is 9. So x squared plus 6x plus 9 is the result of squaring x plus 3 squared. And again, if you've been practicing squaring binomials, that will seem reasonable to you. This would be x minus 1 squared. Half in means I'm going to take whatever number I see as the multiplier of x and take half of that number and put it in the parenthesis. Square out means that as I square the binomial, it'll create x squared minus 2x, but it'll also create a plus 1. Half in, square out. Half of negative 10 is negative 5, so this one would be x minus 5 squared. And the term of completion over here, if you expand x minus 5 squared, you get x squared minus 10x plus 25. So pause the video, do these, start the video again, and check your answers. Now, we're going to use this concept to get something into its vertex form for the purpose of graphing. And typically what we do whenever we see problems like this is we add 0 in some inventive way. So here's the way that we would do this. Now, I like to do it going down the page. So underneath my original expression, I'm going to put a parenthesis with x and a square. And just like previously, I am going to think what number belongs in my parenthesis. So this is where I say half in, square out. Half of negative 6 is negative 3. Now I'm going to expand that and see what happens. It becomes x squared minus 6x plus 9. So I'm going to put plus 9 minus 9. Now, look at the original line of my expression, and you should realize that I've really added nothing. Now, these 3 terms here create x minus 3 squared. These 2 terms here create a result of negative 2. Now, the last 2 lessons that you've done, you've practiced expanding expressions like this to get them into their expanded form. If you've been doing that, then you check your work right now by expanding this and see if it gives you x squared minus 6x plus 7. For this next one, we're supposed to get really quick at this and recognize really quickly that this must be an x plus 4 squared binomial, but the squaring would create a 16 that's not there, so we're just going to put a plus 16 minus 16. So in essence, the amount that we've added is 0. The same previously, these three terms represent my binomial square. So let's just work the 11 minus 16 out into its answer, and we'll have a minus 5. Again, pause the video, see if you can expand that and prove to yourself that the result would give x squared plus 8x plus 11. That's a really important skill to practice. I'll show you why in just a second. Now, I'm going to work the rest of these problems using what I call the Goldilocks method, and you'll see more about that in the next lesson. The Goldilocks method is the question, is it too big, too small, or just right? It's still based on that concept of squaring the binomial and recognizing that our binomial must be an x plus 1 parenthesis squared binomial. But now I'm just going to expand in my head and just speak it through. I think maybe this time I'll just write some numbers down that represent what's going on in my head, but I never write this stuff down, I just think it. So if I expanded x plus 1 squared, it would create x squared plus 2x plus 1. Now I'm going to ask myself a question. Do I like it? Is x squared the correct thing? Yes. Is 2x the correct thing? Yes. Is plus 1 the correct thing? No. It's supposed to be a minus 5. So is the plus 1 that's created by this expansion too big, too small, or just right? Well, it's too big. Now, I think of it as if it were on a number line. I just created a 1 on the number line, but I wanted it to be a negative 5. So 1 is definitely too big. How much too big is it? Well, it's too big by 6. So if I would subtract 6, I know I'd be right. Now, if I was using the previous method, this would have been a plus 1, that's the plus 1 of the expansion, and a minus 1. And the minus 5 minus 1 will be the minus 6. So the Goldilocks method will do the same thing. I'm going to do it on this one. I know that my parenthesis will be an x plus 5 squared. So I'm going to expand in my head and just think what it would make. And it would make an x squared plus 10x. I like that. But it would give a 25. And the 25 is too big. How much too big is it? It's too big by 9. So if I would take 9 off the 25, it would give me the 16. Now again, if you practice the last 2 days expanding the Vertex form, this will make perfect sense to you. Now, here's your assignment over here. You actually have to do these problems on your own. And on your assignment, you have to do this as a graph. You have to first of all create it into its form that shows the vertex form, the parenthesis squared that shows the left-right shift, and then the number on the outside of the parenthesis that represents the up-down shift. So we'd have to go back about 3 lessons to remember that. You might want to go back and look at that lesson again or review that video. But now we're going to talk about taking something that is in its standard form and seeing if we can get it into that vertex form so that we can put it on a graph and see what its graphing behavior looks like. So you have 3 problems like that to practice not only putting it into the vertex form, but also doing the graphical analysis of it, and then state your domain range and the intervals on which the function is increasing and decreasing. So these 4 problems here will be just like the ones beside it. You can use the zero method where you add and subtract, or if you're comfortable with that Goldilocks method, you can do the little Goldilocks method. So the next assignment that we're going to do will take this up just another notch. So we're going to get another layer of complexity on the next lesson. Good luck.